Okay, welcome back to Principles Engineering, and we're back working with our truss. So we've solved for the external forces and the external moments, and we've made those all sum to zero. So what we've done is we've arrived at the reactionary forces supporting the truss by doing that. So now let's choose a point and do a free body diagram. So right now I'm just going to choose C, and it's the easiest of the points, I think, because it's got no angles to it. So let's redraw C. What I'm going to do is I'm going to actually draw C in blue. And for a free body diagram, I've got my point C. And I've got my elements going up. And I'm going to name these elements. So this element is CE. And then I've got BC. And I'm going to put those both into tension, meaning that it's tension pulling on the point C. And it doesn't really matter if we start out in tension or compression. So let me draw my external forces, because if we start out and we assume wrong, what it's going to do is we're going to get a negative sign if we always use this convention up here. Okay. So looking at C, what do I have? I've got 200 pounds pushing up at C. So what I'm going to say here is the sum of the forces in the x direction at C has to equal to 0. And the forces in the x direction are simply BC. So what does that mean to me? It means that if the sum is 0 and BC is the only force, then BC has to equal to 0. So we know that. So I can actually put 0 into my truss diagram, and let me actually do that on the right layer here. So I'm going to go back and erase that. So that'll be 0. Okay, that's simple enough. Let's go back and now let's look in the y direction. And I'll do this one in green. So this just says that the sum of the forces in the y direction has to equal to 0. So what do I have working in the y direction? I've got the reactionary force at C in the y direction plus the force CE has to equal to 0. And I really should draw these, and I think I'll be a little more disciplined here, but I'm going to write that as FCE. So that'll be a little bit clearer. FCE has to equal to 0. Again, this is really simple. All that's saying that is RFCY equals to the opposite of FCE, or conversely, FCE is the opposite of RFCY. Now you can see that I've got an error here. So what I really need to do is to change this force, and this force is going to be equal to a minus 200 pounds, because the reactionary force, CY, is plus 200. So I can substitute these in, and I'll do this now here. So minus 200 equals to FCE. And that just means that that force is actually going down, not up. It's going down. So let's go ahead and draw that right here, and we'll put that onto our master diagram for the forces layout. So what I've got is 200 pounds going down. So that means it's in compression, pushing down. So compression there. Pretty straightforward. So what we've done is we've summed all the forces at C. Now, similarly, I can go back in here and I can look at the forces at A. So let's go back over to A here and give a quick circle around A and see what we have on that free body diagram. Same basic drill. The forces at A, the sum in the x direction has to equal 0. The sum in the y direction has to equal to 0. So drawing A, it's a little bit more complex. I've got my point A, my vector. Again, I'm going to put both of these in tension just to start out with that because it doesn't really make any difference. This is AD. This is AB. External to that, acting down here, I've got a 0 force in the x direction, so all I really have here is I have a 200-pound force up. So what I'm really looking at now is I can break down my vector AD into two different components. I'm going to have ADX and ADY. Now you can see that I've pretty much got that drawn backwards now, don't I? Because I know ADY has to oppose ADX. This resultant vector is going to be not quite what I've got drawn there. That resultant vector would be opposite. So let me put ADX going this way. So ADX looks like it's going to be a negative in the x if I've got AB drawn right. So let's start out and solve the summation of the forces in the y direction. So the sum of the forces in the y direction has to equal to 0. What I've got here is I've got ADY plus the reactionary force at A and the y has to equal to 0, or ADY equal the opposite of the reactionary force AY. Now, using my convention, reactionary force AY is plus 200 pounds, so that equals to minus 200 pounds, so the invert of that, ADY. Kind of makes sense, doesn't it? Now, I know from my geometry that this angle right here, theta, equals to 45 degrees, because when I initially built this, what I said was from A to D is 3 up and 3 over, which makes that angle 45, no matter how we slice or dice it. So now if we think about the formula for the sine function, we can really take ADY and we can solve for AD. And the relationship is a couple of different ways we could do this. We could do it with the inverse tangent, but let's just do it with the sine, because we know that if I've got a unit triangle, and I call this C, A, B, I know that in theta, I know that C times the sine of theta equals to A. Therefore, C equals to A divided by the sine of theta. So what I can say now is AD equals to ADY component divided by the sine of 45. Now, I wrote this as minus 200. What it means is it's 200 pounds going down. 200 pounds going down. So then this means it's minus 200 pounds, and let's just drop that off, divided by the sine of 45. And that ends up being root 2 over 2. So we got 200 divided by the sine of 45. And that means that AD equals to 282.8 pounds. So looking at this, if ADY is going down, ADX is going to the left, I know that AD is actually going down, so that's actually in compression. When I got that negative number, that's what that was telling me. So I'm going to fix that on this diagram, and I'm going to draw the vector AD going down. Now what I can do is I can come back up and I can realign my reactionary forces, or go to my reactionary force layer, and I can put in this vector, which is 282.8 pounds. And that is going down, so that's in compression. Straighten that up a little bit. All right, so what I've done now is I have solved for my reactionary forces in the element, or in the outside of the diagram, and then I've started point by point going through, and I'm not quite done with A, but I have found AD. So now that I've found AD, I can quite easily carry this forward and say, hey, if that's 282.8, guess what? I know what the vector AB is going to be. Because in this relationship, I've got this sine 45 relationship, so I know that this vector right here is 200 pounds. And let me actually draw it like this. I know that's 200, so guess what? I know that's 200. And that's just because it's a 45-degree angle. So let me go through and do this the mathy way, though. So let's go through and do it a little bit more mathematically complete. So what I've just said is, here's my vector A, my point A, and I've got this force coming in compression, AD, and it's 282.8. And I've got a resultant force here, 200. And what I've just said here is, when I break this down into component forces, which is how we arrived at that 282, I get a y component, and in this instance, I get an x component going to the left or going negative. So I know, because this is 200, because it has to counter the force pushing up, I know that this has to be 200, because this angle is 45 degrees. Mathematically, I could also say the same unit triangle, C, A, B, and I could say that C theta times the cosine of theta equals to B. So what I can do is take 282.8 pounds times the cosine 45, and lo and behold, I get 200 pounds. There's a little bit of a rounding error there. Don't get too spun out about that, but 282.8 times 45 cosine and I get 199.78, but it's 200 pounds, just a little rounding error. So I have just solved at point A. I know that the only other vector force that I have working here is the force AB. So I've just said my force is in the x direction equals to 0, which then equals to AD in the x direction plus AB equal to 0. And I said that ADX equals to minus 200 pounds. Therefore, AB has to equal to plus 200 pounds. I can come back and I can put that on my force layer in red. Now it's going to the right, which means that it is in tension. And that's where we'll stop on this one.